welcome to today's webinar titled Design for Six Sigma, a Roadmap for Excellence. I'm Isha Gupta, Marketing Manager at Geometric Limited, and I'm the moderator and host for today's webinar. So first of all, I'd like to thank everyone for taking time out to attend the webinar. And as I can see a high turnout, I believe there's an increasing interest to understand the Design for Six Sigma philosophy. So in today's presentation, we will talk about Design for Six Sigma concept, best practices, tools and techniques for its successful implementation into product development. So with this, let me introduce the speakers. Our first speaker, Vikram Bhargava, is a global engineering consultant and trainer. He has over 40 years of experience in product design, development, manufacturing, and management, especially in plastics. He's a fellow of Society of Plastics Engineer and past chairman of its Product Design and Development Division. Vikram has recently retired as the Director of Mechanical Engineering Services at Motorola, where he was heading a large group of engineering professionals. In Motorola, he successfully led several Six Sigma projects with millions of dollars in savings and is a certified Motorola Six Sigma Black Belt and trainer. He has trained thousands of design engineers and suppliers on plastic part and assembly design worldwide in US, Canada, China, Taiwan, and India. He holds over 21 international patents. Vikram is currently authoring a book on robust product design, which will be released early next year. So with this, I would like to thank Vikram for being with us today. Our next speaker, Prashant Chandanapurkar, is a domain expert in the field of design for excellence at Geometric. He's a mechanical engineer and holds a master's degree in operation management. Prashant holds a Six Sigma Green Belt and has worked on multiple engineering projects in the area of process improvement. Prashant holds a wide experience of working with diverse industries like consumer durables, energy, and industrial equipment sector. So before I hand it over to the speakers, let me also quickly explain the logistics of the webinar. Webinar is approximately 60 minutes. All attendees are in listen-only mode to avoid any background noise, but we do, of course, welcome your questions. In order to submit your questions, simply type in using the chat window on your GoToWebinar console, as you can see on the screen. We will answer as many questions as possible as the time permits in the formal Q&A session, which is during the end of the presentation. We are also recording this session and will send the link to the recording next week for those who missed it or would like to see the presentation again. So without further ado, let's begin the presentation. I will hand it over to the first presenter of the day, Vikram Bhargava. Over to you, Vik.
Thank you, Isha, for that very kind introduction. Good morning, afternoon, or evening, depending on where you're calling from. And thank you again for attending this webinar. So, you got to implement a Six Sigma program or else you're doomed. Aren't you the same consultant who sold us the worthless TQM program a few years ago? I assure you, sir, that this program has a totally different name. When can we start? Funny, right? Not really. The sad fact is that a lot of companies have started Six Sigma because it's the fad of the day or to use it as a marketing tool to promote the company. They have spent hundreds of thousands of dollars and a lot of effort without getting much in return. My point is, if you're going to be successful with this powerful technique, you need to make it a part of the company culture, right from the top at the CEO level to the lowest level worker. Let's go into a little bit of the background of Six Sigma. In the 80s, Motorola decided to provide an extra margin to the customers with more robust products. They did this by controlling their processes so that the standard deviation, or S, of their process was 1/12 of the difference between the upper specification limit and the lower specification limit. And the drift of the process from the target was no more than 1.5 sigma. When the process meets this criteria, the fraction of parts falling outside the range from the USL to the LSL is at the most 3.4 parts per million. Almost 1,000 times improvement over the traditional approach of 3 sigma where it was 2,700 parts per million. Let's look at it a little graphically. Let me put my cursor on. Okay, so here is the lower spec limit for the design. Here's the upper spec limit. And as you can see, between these two limits, we can fit in 12 sigmas. Here's the target. And ideally, the nominal of the process would be right at the target. But that is not practical. So they allow a shift of 1.5 sigma on each side. 1.5 sigma on this side, 1.5 sigma again on this side. Again, under these conditions, we will have not more than 3.4 parts per million out of spec parts. A little bit about the evolution of Six Sigma. Today, it is the structured application of tools and technique applied on project basis to achieve sustained strategic results. So if you go from the left to the right, this is the literal Six Sigma that we started with, to the middle where we use the DMAIC and DMADV techniques once in a while, and I'll talk about these techniques in a few slides, to making it a part of the management system and driving a vital few, having dedicated resources, having data-driven decisions, and having being customer focused. You can see the impact on the business is a lot more dramatic here versus using it as a tool in manufacturing to reduce the number of defects. Aimed at the big whys. If you look at a mathematical equation, a common equation is y is equal to x1 plus x2 plus x3. If we consider the y as an important mission for the company, in this case, a profit improvement, it's a function of x1, which is selling cost, x2, which is the product cost, x3 warranty cost, and so on. In order to improve y, which is a dependent variable, we have to focus on the independent variables, the x1, x2, and x3. We start with the biggest x and move on down to the smaller x to get the desired shift in y. It requires active participation by all levels of personnel. The methodologies used are DMAIC, DIDOV, DMADV, DMADV, which was started by Motorola. Today we are going to just concentrate on the DMAIC and DMADV techniques. Six Sigma applies to all functions and product development, not just manufacturing. It can apply to human resources and marketing and legal department, every single department of the company. It consists of a team approach consisting of the sponsor, who is a very senior person, making sure resources and our funds are available for the project. The second member of the team is the champion, who is typically the manager of the department where the project is being conducted. If it's a HR project, then the vice president of human resources may be the champion. A black belt who has extensive Six Sigma training and multiple project experience, and or a green belt who has had some Six Sigma training and has project experience sufficient for the project under question. There are other team members representing other departments that can be quality control, marketing, engineering, and so on. And then it generally consists of subject matter experts, SMEs, from engineering, from quality, from marketing, and from industrial design, and so forth. So how's Six Sigma versus traditional methods? If you look at the purple line at the bottom, normally in a production process or in any given process in an organization, there's a problem. We have a group of people look at the problem, find the root cause, fix the problem, we move on till we have another problem. We have a group of people, again look at the problem, fix the problem, and move on. And in the process, we might get some overall improvement. If you have heard of 4-8D, that's one such technique, basically looking at the special cause, causing the problem, fixing it, and bringing it back to status quo. DMAIC is a continuous improvement. We look at the big axis and address the big axis and have a continuous improvement. DMADV, on the other hand, is a complete redesign of the system. So let's take a look at a common example. The railways, if we stuck with a steam locomotive, we would have a problem with the derailment or with the engine breaking down. We'd have people and engineers look at it, fix the problem, and again bring it back to the original condition of operation. If we wanted to go beyond the steam engine, we would go for DMAIC, which is continuous improvement. We would look at newer locomotives. We would look at better tracks. We would look at better signaling system. We would look at better training. And if we wanted to completely redesign the system, we might go with a bullet train. So let me give you the example of China. China, about 15 years ago, had probably the worst railway system in the world. They did not were not satisfied with status quo. They were not even satisfied with making it as good as the other railway systems in the adjoining countries. They were going for something big with a completely new design. Today, they boast of the fastest train operating in Shanghai between the airport and the city center. Here, the x-axis is the relative time. In the case of the huge railway system, it may be in years, 3 years, 6 years, 9 months, and 9 years and 12 years. But on a project within an organization is probably in months. So you can see a DMAIC project bringing you about 50% improvement in about 12 months, and a DMADV project bringing you close to 75% improved within 3 to 6 months. The DMAIC process. This is used to improve an existing process. The examples are poor yield, high cost of manufacturing, poor customer satisfaction, and so on. We define the opportunity, what is important to the customer and the stakeholder. We measure the current performance. We analyze the opportunity, what exactly is wrong with this process. We improve the performance, basically what needs to be done to make it better. And then once we've improved the performance, we've put some controls in place to make sure that we hold the gains and that we don't go back to the old process. This can be control charts or other control techniques that various companies use. That's all we are going to talk about DMAIC. Now we'll move on to DMADV, which is designed for Six Sigma. This is used to create a new product or a process. Just not a new product, it also is used for new processes. Again, define what is important to the customer. Develop measures of success. At the end of the project, how will we know that we are successful? Analyze and identify new concepts. Design various alternatives. And at the end, verify and make sure that we guarantee the performance going forward. Let's take a deep dive. Define. Understand the customer's needs. And the customers, I don't mean only just the paying customers who pay for your product. I mean internal and external customers. The internal customers may be the electrical engineer who are going to put the PC boards in the cell phone cover that you've just designed. Or it may be the assembly shop, or it may be the molder, or it may be the tool maker. We have to take care of their needs. Identify their critical requirements. It's called the CTQs, critical to quality. That could be cost, minimum guaranteed performance. The phone should not bend if we should sit on it. weight, reliability, etc. Translate needs into measurable and actionable parameters. This is one tool that we use. It's called quality function deployment, and we'll talk about it in a couple of slides. As a team, we obtain consensus on the goals, and we conclude with a design document which serves as a set of specific and specific sets of deliverables for the project, including scope, schedule, and budget. Here's an example of quality function deployment. We're designing an internal bracket for a cell phone. What are the customer needs? It needs to be durable, it needs to be lightweight, it needs to be low cost, and the aesthetics should be good. What is the importance to the customer? This is on a scale of 0 to 9. Durability is very high, lightweight is fairly high, low cost is somewhat high, and aesthetics, since it's an internal member of the phone, internal component, it's not that high. If it was an external component, the aesthetics would be very high too. And then we look at the various factors that we as engineers can control. We can control the material, we can control the design, we can control the processing, and we can control the tooling. What is the relationship between the customer need and the factor? This is measured in 9, 3, and 1. 9 is a strong relationship, 3 is a moderate relationship, 1 is very little relationship. Don't ask me why they choose 9, 3, and 1, but that's what the industry uses. So now we can see the durability, the material relationship to material is not that significant, but the design is very, very significant. The processing is not that significant, and tooling is not that significant. Moving on down the line, aesthetics, the material is not that important. Design is very, very important. Processing is very important, and tooling is somewhat important. So if we multiply the importance by the relationship factor and sum it up in this column, we see the feature priority. So we look at the feature priority here. Design is the most important with 183, processing is the next, and material and tooling follow. So if we are to really take care of the customer needs, we'll address design first, then processing, then material and tooling. We move on to the measure stage. We establish specifications. These can be functional and ruggedness, in terms of drop height, in terms of water ingress. We establish and commit to a budget. The budget is very, very important to our internal customer, the stakeholders. And we identify potential process issues and proactively come up with measures for preventing these issues. The next stage is analyze. We identify concepts for the new products or process. We challenge assumptions and paradigms. This is extremely important. We don't have a system where the person with the loudest voice wins. Everybody's opinion is considered. Nothing is off the table. We don't reject ideas because we've never done this before. We have to break the paradigms. Once we've done that, we narrowed them down to a small list of proposals. We move on to the design stage, and the main goal here is to come up with robust solutions. There are some tools like failure mode and effects analysis, which I'm going to show in the next slide. We benchmark against the competitor. We do tolerance analysis. We do simulation in terms of, in plastic, we do flow simulation, and the most common tools are mold flow and Moldex. We do structural analysis and so on. And once we know that the simulation shows that the product is pretty good, we do actual prototype testing. A quick example of FMEA. In this case, we are designing an external case for a cell phone. So what is the function of the part? It holds the internal parts together. It prevents water ingress. It provides aesthetic appeal. What is the potential failure mode? The case may crack. It may get scratched. It may there may be a seal failure, and there may be flow marks from molding it which may not appeal to the customer. What is the potential effect of the failure? Internal parts are exposed, loses aesthetic appeal, possible loss of functionality depending on the amount of water that went in, and obviously very poor consumer appeal. What's the severity? Obviously, if the phone cracks, you might as well put it into the junk pile. If it's got a minor scratch, no big deal. If the water gets in, you can dry it with a blow dryer, I think, and the phone may still work. But if it has very poor aesthetic appeal, it has flow marks and flaws on the surface, you're not going to get too many customers buying the phone. How do we prevent it? What are the causes of it? Improper processing in the case of plastic, poor drying, normal abuse, exposure to high heat and humidity, and poor design in the case of aesthetics. What are the chances of it occurring? We can be, it can crack. There's a good chance that it can crack in a drop. Maybe not that great a chance of getting it getting scratched if you handle the phone carefully. Again, if you handle the phone carefully, the water may not get in. But the chances of the appearance not being adequate is very, very high. What are the controls for the process? We control processing. We control scratch resistance. We control it with scratch resistant coating. We do seal testing at elevated temperatures and humidity. And we check design for errors. How easy is it to detect this defect? In the case of a crack, we might not even detect it till the actual failure occurs. The scratch, we can detect it fairly easily. Seal failure, we may not be able to detect till actually the water goes in. And the flow marks is very easy to detect. It's obvious that the surface is not right. We multiply these three together, we come up with a risk priority number. And we address the biggest one first. We start with the crack issue, and then we go to the water ingress issue, then we go to the, we go to the aesthetic issue, then we go to the water ingress issue, and finally to the scratch prevention issue. Verify. We verify that the design based on small runs. They can be done in labs. They can be functional testing, and they can be beta testing with actual customers. We set up small pilot runs. We implement the final production process, and we hand over the production process to the process owner, which is manufacturing. One important thing is, as engineers, we stay involved and the manufacturing process is steady state and in total control. With that, I will invite Prashant to talk about DFX. It's a very powerful tool that you use at every stage of the DMADV. Prashant?
Yeah, thanks, Vic. So thanks, Vic, for the overview of Six Sigma. And we had this sort of a deep dive into DMADV process. And I'm sure now, my friends who are from design engineering are sitting there, and their immediate question would be, how do I implement DMADV in my product design process? Many times they say that we do have these requirements documented, but we can't really predict these kind of results or what will happen to those critical to quality parameters, unless we reach to the prototype stage. And there could be some questions like, we do have this in-house practice, but we don't know, is there a better way to do it? And yes, there is a better way to do it, and that's what I'm going to show, that how you can leverage this geometric DFX solution to achieve your results. Now, what DFX is it stands for Design for X, or Design for Excellence. It's an extensible, flexible, and scalable framework which is provided by Geometric. And what it does is that it takes into consideration all your critical to quality parameters organizational guidelines, it could be standards, or it could be even some of the best practices which are followed globally, and that it provides as an input to a design engineer. So what it is nothing but a design assistant solution, wherein it can give you feedback based on the parameters you set up and the desired result or outcome you're looking for. So I'll just give a quick overview about how this DFX framework works and how it can help to achieve the desired results out of Design for Six Sigma. So if you look at this framework, I'm sorry, it's a little bit complicated, but if you pay attention to the pointer here on the left bottom right side, you can see here source of DFX guidelines. So what DFX is that it starts with some of the rules. So these rules are nothing but all those critical to quality parameters what we saw earlier, and those parameters are documented and converted in form of rules, which are nothing but measures and values applied to it. These rules then go and fit into the DFX systems, where it's further classified into based on different manufacturing process. So for example, it could be the kind of part you are working on it. It could be a milling part, it could be injection molding part, it could be sheet metal, and it could be even assembly as well. So it will depend what kind of a part you are designing. And after you take that part into your CAD system, basically where you start designing that part, this DFX frameworks goes and sits into the CAD system. And what you finally see here is a product called DFM Pro from Geometric. So a lot of things which happens in the background, but believe me, for designers we have made life very, very simple. How you work with this solution and how you execute your checks. So as I talked about rules, let's take a case or a live case how to use DFM Pro solution in real life with a use case. So I'm going to go back to what Vic has left with the DMADV process earlier. And if you look at those steps, the first step, really the define stage, where we define all those critical to quality parameters. If I look at the critical to quality parameters, and let me take an example of a plastic component again, and see that there could be various measures and quality parameters for a particular set of a parameter. So for example, if I take thickness as my parameter, I choose thickness, and now what I'm going to do is that I need to assign some measures for it. Now this thickness could be measured into various areas. So it could be sudden wall thickness measurement, it could be wall thickness variation, it could be uniform wall thickness. The next step what I have to do is that when I have to establish measure for each of this parameter. So if I take sudden wall thickness, sudden wall thickness is nothing but in plastic components, the thickness of the component should not drop suddenly, because if the thickness drops suddenly, what will happen is that it could lead to bad quality of the plastic part, it could lead to sink marks, and you will not be able to achieve the desired fitness of the product you are looking for. So it is important that you parameterize these requirements and put it as a check, and keep it something which is measurable so that you can go back to them and change those values and you can get the desired results. Moving on, once you put this parameters into measure, you move to analyze. Now typically what designers do in this stage is that you are evaluating various concepts, and this is probably at a very broad level. So this could be probably exploring different type of materials. It could be even different type of a shape, and basically evaluation of different concepts. And then you reach to a certain concept that okay, this is the best option, this is the best concept I would like to select from my design. Then you actually go and start the detailed design process. So here at slide 24, what you're seeing is that I'm working with the CAD system, and what a designer is doing is basically there are two things which are happening simultaneously, that I'm designing something and I'm simultaneously verifying my design. So this is what we call as typically a collaborative process where the design and verification happening simultaneously, and that's what we call the iterative process, or the nature of the design process is iterative. And here the designer is looking for sort of a live feedback on the design. Now let me go to the real world and probably share a quick case how this can be used for injection molding process. So are you able to see my screen here? Yeah.
Yeah, we can.
So yeah. So here in Pro Engineer window, I have opened one plastic component, and you can see that this component is open. I clicked on DFM Pro, and you can see that it's integrated into the CAD system. So I just hit start, and here there are various inputs which are required. So here, I'll come back to what this rule is and what it's designed for. I just click on the input. So I click here and take injection molding or plastic molding as an example, and just hit the run button. Now the system is smart enough to, for example, for plastic part, what input required is that what is the pulling direction for the plastic part. So it will take that pulling direction and hit finish button. It will automatically extract all the features which are required for the critical to quality parameters, and based on that, it will present the results to a designer. So all the red crosses, what you see here on the screen, those are the areas where it is not meeting the producibility criteria or the critical to quality criteria that has been defined. And below here, what you see is that there is a green tick, which is nothing but the checks what we've been defined, and those checks have passed. I can sort out this result based on the criticality. So let's say if I've assigned a criticality here, which is medium and high criticality, and now I can further drill down and find out what are those design features which are not meeting those CTQ parameters. So I just click here, and you can see that the system provides me a result that this is the area where there is a variation in the sudden wall thickness. So you can see here it provides a feedback, and I can further zoom to this area, and it is depicted here on the screen. So what DFM Pro is doing here is really it's doing three things. A, it is highlighting right on the model that where the exact problem is. Second thing, it's showing that what kind of an issue and problem it is, and the third thing is that how you can correct it. So here in this case, you can see that it has measured the thickness, it has calculated the gradient, and it is also giving feedback. So here you can see that the actual value of gradient is 0.45, and the recommended value is, it should be less than 0.3. So this way, it provides results live right on the screen. Then as a designer, I can quickly go back and change values of these parameters. The second thing here is that I can go here and select another parameter. So for example, here I go and I select a minimum radius at the base of the boss parameter, which has failed. So I can go and click here, and you can see that it has automatically highlighted this boss feature. And what it is showing on the screen is that there is a boss which is designed, but there is no radius or corner radius that needs to be provided at the bottom of the boss. So what happens is that during a loading condition, when you're going to put a fastener here, it's going to put this boss feature into a lot of stress. And if there is any load which is coming perpendicular direction, it will break here at the bottom. If I would like to know more information about these features, I can just right click and click on help, and you can see that it provides further feedback about what is that particular feature I defined as a critical to quality parameter and what is the input required. So similarly, there are multiple such conditions. For example, here mold wall thickness, which depicts that I need to maintain enough distance between the two features, because if I don't maintain enough distance, this could lead to a thin steel condition, and the part might break during operation. So this way you can see that this solution provides a live feedback to a designer even before you go to the next step. The way to define it's pretty simple, that when you start with the DMADV process, you click edit button here, and in the beginning it will pop up a screen wherein you can go, and so for example I have defined certain values for certain wall thickness variation. I can double click here and assign those particular values. Similarly, I can go to another instance, and you can see here that there is another check where I can go again and change my values or configure my values based on the check or critical to quality parameter required. And this way I can connect, select and deselect any check I want and just execute it. And this way you can see that it's pretty simple. It makes life very easy to actually implement DMADV process with DFM Pro. I think there are a lot of other features depending on different manufacturing processes and parts, and that can be, you can further explore. So if you visit www.dfmpro.com website, you will find further information about this solution, and there is a lot of information which is also available on the site regarding the product. Since we are sort of running out of time, so I'll quickly hand it over to Vic to explore and provide some more information about the tool. So over to Vic.
Thanks, Prashant. Ishak, my screen is visible?
Yeah, I've just made you the presenter, Vikram.
Okay. So simulation is a very important critical step in design. But simulation assumes that the material properties used in the analysis are reliable, and that the cross-sectional areas and wall thicknesses used in the analysis will not be changed more than a minimal amount as a result of the simulation or other changes to the part. If a plastic part is not designed for the established rules, there may be huge molded-in stresses or stress concentrators that the simulation will not even capture. If you look at the picture on the right, here's a part. Let me get my laser pointer here. Here's a part where the thickness on the right side is twice that on the left side. And as it comes out of the mold, this is infrared thermal photography, the temperature on the left is 118 degrees. The temperature at the right is 238 degrees. The right will continue to cool for a long time, cool down, resulting in a very high stress here. This will not be captured by normal simulation software and has to be captured by something like DFM to make sure the design rules are followed. The other thing that will happen if the drifts are very high and thin and the simulation results determines that the plastic will not flow into these areas, and then you have to go back and redo the rifts, you'll have to pretty much do the design all over again, because now you've completely disturbed the spatial arrangement for the components around it. So therefore, it is best to run DFM Pro to make sure the design is sound before any detailed simulation is performed. In one of the companies that I worked for, I was in charge for simulation, and I pretty much made it a rule to run DFM Pro before any simulation was done. Some other commonly used tools in the Six Sigma process. Pareto Analysis. Pareto Analysis should not be new to most of the people attending today. Basically, it distinguishes the vital few from the trivial many. Arranging data on a Pareto chart highlights the vital few and separates them from the trivial many, and thus we set priority to our efforts. This is an example of common plastic part defects. It's somewhat of made up, but not that atypical of a plastic part. We can look at flow marks defects as being 40%, sharp internal corners being 20%, warpage being 10%, sink marks 7%, and so on down the line. And there's many others who are 10%. But again, if you look at these three defects, visual defects, sharp internal corners, and warpage, that accounts for 70% of all the defects. And if we fix them, we will make a substantial difference to the quality of the part without putting in too much effort. And one of the good things that will happen is, as a result of fixing these three, many of these other defects will be improved in turn, just as a consequence of fixing these first three. 5 whys. You ask a question 5 times and you come to the real root cause of why something was caused. My granddaughter, who's 5 years old, is an expert at 5 whys. why grandpa, and she keeps asking me why till she knows the real answer. But applying it to a plastic part, here's a microwave cover that, my own microwave cover that's cracked along this line here. So the engineers asked themselves, why did the cover break? Well, obviously the part is weak. Why is the part weak? Because the stress is very high along the line of failure. Why is the stress very high along the line of failure? Because the inside radius is very sharp. Why is the inside radius very sharp? Bingo! The designer is not aware of the minimum corner radius requirement. Again, using DFM Pro, it would have made sure that you were aware of it. Here's a real quick engineering background on why sharp corners result in failures. As the radius increases or the radius decreases, there's a thing called stress concentration factor. Here we are reducing the radius at the corner here, and as we reduce it, the stress concentration factor goes up dramatically, and when a part does fail, it basically determines the position which it will fail at, which is at the corner. Here's another powerful tool, cause and effect diagram. It's also called the fishbone diagram and in the Ishikawa diagram. If we look at any defect, in this case visual defects on this plastic part, we can break it down into 4 traditional causes: machine, method, materials, and man. And recently we have started also looking at the measurement system and the environment around the molding process or the production process. We look at the various causes and see what possibly caused these flow marks to occur. We can look at the method, which is the processing, which is the molding machine, molding the parts. The barrel temperature was high. The material was not dried poorly. Was dried poorly. The injection speed was too high. But after we have looked at all of these possible factors, the most prominent factors are uneven wall thickness and pigment quality. The pigment didn't quite mix with the plastic resin and caused the appearance to look not acceptable. KANO analysis is used for your product to stand out from the competitor. Basically, you look at the features and you look at the performance. So if you look at a car, you look at its features and its performance. And they're basic features without which you're not going to sell one single car. And then a feature may be power brakes, and even Bluetooth connectivity for your phone lately has become a standard feature. You look at performance, you need to get at least 25 miles a gallon or X kilometers per liter. And you can put in some exciting features into, like an anti-collision system where it will prevent a vehicle in front of you and stop even if you've dozed off. That creates excitement about the product, as long as the cost is obviously not too high. So if you want to stand, if you're in this box here, your product does not really stand out from the crowd, and you're one of the many. But if you really want to stand out from your competitor, you have to go north on the features line and northeast on the performance, and then you're going to stand out from the competitor and be able to sell your product more than them. The next tool is POKA-YOKE, which is the Japanese for mistake proofing. If you want to plug in your the connection into the socket and only in one direction, where this is the positive and this is negative, otherwise you'll have a blown circuit. You have to have some mechanical means of making sure that doesn't happen. So in the top instance, you can plug it either way, and nothing will prevent the user from doing it. But on the bottom one, you can plug it only way. It's a POKA-YOKE. Take the example of a simple label on a plastic part. Most of our production is done in China these days, and most of the Chinese operators don't even know the English language. So if they didn't know, if there was no POKA-YOKE built into it, they could possibly put that label upside down. this cut corner on the plastic part and the cut corner on the label, make sure that these two have to match when you put the label in, and you're not going to put a label upside down. A POKA-YOKE. And here are some concluding thoughts. Challenging the paradigm. In 1530, Copernicus said the Earth moves around the sun, and the belief till then was that the sun moves around the Earth. For this blasphemy, Copernicus was actually burnt at stake for challenging the paradigm. Galileo supported Copernicus. He was made to apologize publicly and was put into jail, in a jail for the rest of his life. Paradigm shift is important, is difficult even today. When the person who first thought of a fluorescent lamp replacing a filament lamp, when he brought it to his peers, I'm sure there was a lot of resistance. This will never work. It'll cost too much. People will not like the form factor. It'll be too expensive. The electronics will not fit in this form factor, and so on and so forth. Guess what? 15 or 20 years from when it was first devised, the filament lamp is headed for the history books. Big, hairy, audacious goals. Be hags. Challenge yourself into going way past your comfort level and come up with a product that is totally unique. And the biggest example that I can remember in the last 50, 60 years is John F. Kennedy. In the late 50s and early 60s, Russia or the Soviet Union seems to have been winning the space race. So on May 25, 1961, John F. Kennedy stood before the Congress and said, "First, I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to Earth." On July 20, 1969, less than 10 years from then, Neil Armstrong and Buzz Aldrin became the first humans to land on the moon and come home safely. In the 50 minutes or so that we've had in this presentation, we could barely scratch the surface of this fairly large subject. We do hope that we have left you some with aha moments and ignited some thoughts to explore Six Sigma on your own. We thank you for your time.